Okay, we can continue. Sorry for that. There was a disruption with internet. Please, we can. Okay, so let me continue with the solution. So now, here we have the integral. After we're integrating the third example, which is the integral of 4 times squared of 4x dx, where if we use the trigonometric identities, so what we're going to get is tan squared of 4x is equal to sec squared of 4x minus 1. So where there is tan squared of 4x, we substitute with sec squared of 4x minus 1. Then by linearity property, we are going to have sec squared of 4x dx minus the integral of 1. So then from which, now if you look at the integral of sec squared of 4x, this is equal to, so we have 4, so this is equal to tan squared of 4x over 4, sorry, tan of 4x over 4 minus x plus c1. When we expand this, we are going to get tan 4x minus 4x plus c. So that would be your the integral of tan squared of 4x. I think if you look at the solution which is given in your notes, it's a bit different. So there was just a typo there. It was tan squared of 4x. So not supposed to be tan squared of 4x, it's not supposed to be tan 4x. There was a typo which needed to be rectified, and I've rectified it. So now, the other examples, please, you can handle them at your own time. Of which I just need to give you one. Now, the issue here is that there is this concept in which we are doing the trigonometric kind of substitution, or rather, there is the situation where we are using the trigonometric identities kind of substitution. Now, my internet again goes, it comes, okay. Oh dear God. What should I do here? Okay, now, the issue is what happens if you have such a situation like this one. So there's a concept that I need to explain really to you is what happens when you have a situation like of which this is theorem number 25 applied by a sine function of power 1 or vice versa then the integrals then of power less than 1 should be the statement should be of sine power. Whenever a cosine is multiplied by a sine of power less of power less 1 or vice versa, then the integral, then the integrals may be determined by, okay, so if you have this situation whereby you look at the cosine function is multiplied to the sine function and the power of the cosine function is less 1 than the power of the sine function or vice versa, then the integral of sine to the power n of x times the cosine of x with respect to x, this is just equal to sine the power n plus 1 of x over n plus 1 plus c. 2, the integral of cosine the power n of x times the sine of x dx, this is equal to the negative of the cosine n plus 1 of x over n plus 1 plus c. So these are standard. You need to make sure that you remember them if you want your work. If you are given this question that you feel differentiating, integrating it is so tedious for you, then you apply these concepts, please. You just need to apply the power sine of power, I think of power 1 or vice versa. The statement was correct. Whenever the power of a cosine is multiplied by a sine of power 1 or vice versa, or a sine of any power multiplied by the cosine of power 1, then the integrals can be determined by these two formulas. So the integrals can be determined by these two formulas. Okay, let's look at an example. Let's look at two examples. Then we need to go to trigonometric substitution. So let's look at two examples. This is example number 26, which I'm going to combine with example number 27. We are saying find one, the integral of sine squared of x times the cosine squared of x dx. The second one is the integral. The integral of sine squared of x times cosine 4 of x dx. The third one, which I will not continue giving you, I'll just write 2 more. Please, then that will be, I think 1 will be more than enough. The integral of sine 3x times the cosine of 2x dx, even though this one also we have to use the idea of trigonometric identities, please. I think I didn't just spot this one. Okay, okay, we can start with our solution. I hope everyone is ready and everyone has joined. That's my prayer. Okay, now, the question is, the thing is, it's not like just because you've seen it has been written in that form, and then you just go direct and start saying, this is equal to this. No. We don't do that. You need to look at the situation. What is the situation at hand? So we start with sine squared of x times the cosine squared of x. Was it sine squared of x, cosine squared of x? No. Supposed to be the power 3. This one was supposed to be power 3. Yeah. So it's supposed to have a power 3 there. It was supposed to be sine squared of x times the cos cubed of x. Now, when you're given such kind of equation, your main goal is to make sure that one of these is raised to the power 1. This is your main goal. Your main aim here is to make sure that you rewrite the whole of this function. You need to rewrite it. That's when you can apply this theorem that I've given you here, which is theorem number 25. Now, how can we do that? Note that sine squared of x times cosine cubed of x, this is the same as sine squared of x times cosine squared of x times cos of x, because the cube of cos x cubed is cos x squared times cos x. Now, using trigonometric identities, this is the same as sine squared of x then 1 minus sine squared of x, where there is cos squared of x, we substitute by 1 minus sine squared of x multiplied by cos x. When I multiply this by this, by that, what you're going to get is sine squared of x minus sine the power 4, sine x power 4, because sine squared of x and sine squared of x to give us that. Then in this side we have cos x. Again, if we continue expanding, then what you're going to get is sine squared of x times the cosine of x minus sine power 4 of x times the cosine of x. Now, after you rewrite everything like that, then you are now home and dry. You can start now finding your answer using that general formula that I've given on the board, that formula that which I've given on the board. So now, hence, then if this is the case, then the integral of sine squared of x times the cosine squared of x with respect to x, this is just the same as the integral of sine squared of x times the cosine of x minus sine power 4 of x times the cosine of x dx. Okay. Hence, using linearity property, this is just the integral of sine squared of x cos x dx minus the integral of sine x power 4 times the cosine of x dx. Now, if you look at a power of the sine function x has been multiplied to a cosine function of power 1, a sine function of power 4 has been multiplied to a cosine function of power 1, this means we can use now that theorem to do our calculations. Hence, now this is equal to, this means this is equal to sine. Now in this case, in the first part, our n is equal to 2. So it is sine n plus, sine x to the power n plus 1. So it will be 2 plus 1 x over 2 plus 1, then minus, there it will be sine 4 plus 1 over 4 plus 1, then plus c. Okay, so this is what we're supposed to have. Then, this will give us, so by simplicity, this is sine power of x power 3 over 3 minus sine x power 5 over 5 plus c. Then you are done with your computation. That is your final answer. Okay. Next, I think from the look of things, the next one we can make the sign anyway. We can make the sign. We can change the sign function in that simplified manner. But if we change the sign function, then we'll have a problem. But either way, I would wish you to go and handle it. Maybe I'll handle the last part of the example. Like I mentioned, it's not like every example that I put there, it will be handled. But for part 2, Part 2, I'll just leave it as an exercise. That's a task. I would like you to handle that one. I'll go to part 3. So part 3, it's the integral of sine 3x times the cosine of 2x dx. This is also another part that I need to explain to you because it's very, very important. Maybe let me take you back to, can you remember the half angle formulas? The half angle formulas. Those who can remember the half angle formulas, the double angle formulas, the half angle formulas, those things, please, what you need to do is you need to recall those concepts. If you can't recall them, then it's very difficult. You will not know what you're supposed to do. Maybe I just need to make something. I need to recall something here before I start solving this. A lot of you, maybe with trigonometry, you had challenges, but still, you need to go back to those concepts because these are the questions that comes in an exam anyway. Some of these questions. So make sure that you try to go back to what you were doing in trigonometry. Maybe I would love to take you back a bit. From the normal trigonometry. I hope everyone is following. Let's look at the trigonometric functions. Generally, the sine function, the double angle sine function. We said, recall that sine, okay, I wish you to recall that sine A plus B, this is equal to sine A times cosine B plus cosine A times the sine of B. Also, the sine of A minus B is equal to the sine of A times the cosine of B minus the cosine of A times the sine of B. This is what you learned. Now, the question is, if I add this to this, what are we going to get? This is the first question that you need to ask yourselves. This plus this, what do we get? What is this plus this? This means when I add these two, what will happen is that sine A plus B plus sine of A minus B, I'm adding this plus this, so it will be sine A cos B, isn't it? Plus cos A sine B, then plus sine A cos B minus cos A sine B. If you see, we have cos A sine B, it will be cos A sine B plus minus cos A sine B, they will cancel. Then sine A cos B plus sine A cos B. So in general, when you add these two, what you're going to get is 2 sine A cosine B. Okay, it will be 2 sine A cosine B. If we add, adding gives, this is what we are going to get. When you add, this is what you're going to get. Now, if we simplify this, this means sine A cosine B will be equal to 1 over 2, we divide through by 2, open bracket, sine A plus B plus sine A minus B. So this is what you're going to get. Now, let's go back, rewind back to what we started with. Let's go back to what we've just started with. Now, because of this kind of an identity, if you compare this term, sine A cosine B is the same as sine 3A. In this situation now, A is equal to 3x, our B is equal to 2x. Okay, so this is what is happening. So if you compare this to this, now then, because we can't manage to integrate this directly, we need to substitute this by this kind of a term. Okay, how can we do that? Okay, applying trig identities. Okay, so what I'm trying to say is, I'm going to wrap this now because it's not really, I've already made you to recall. Still, by trigonometric identities, so by trig identities, by the trigonometric identities, this sine 3x times the cosine of 2x is just the same as 1 over 2, okay, sine, our A in this scenario now is 3x, so it will be sine 3x plus 2x, then plus, is it plus or minus? Yeah, there's a plus, sine, okay, 3x minus 2x. If we follow this, when we reduce this, this will reduce to 1 over 2 multiplied by sine 5x plus sine x. Okay, this means the integral of sine 3x times cosine 2x with respect to x is the same as the integral of 1 over 2 sine 5x plus sine x. Thus, the integral of sine 3x times the cosine of 2x dx, this is equal to the integral 1 over 2, which is multiplied by sine 5x plus sine x with respect to x, which is equal to 1 over 2 by linearity properties sine 5x dx plus the integral of sine x dx Okay, so We continue. So now, the question is, so this is equal to 1 over 2. The integral of sine 5x is the negative of cosine 5x over 5 plus the cosine, the negative, which will give us a minus of sine x plus c1. When we expand, let me rewrite it using black. Okay, this is equal to 1 over 2 cos 5x over 5, or it's a negative, minus the cosine of x plus c1. When we multiply through by half, what you're going to get is the negative of cosine 5x over 10 minus the cosine of x over 2 plus c. Okay, that's the end of that question. Now, the next thing that I would wish you to explain to you is where we use the trigonometric substitution. We have looked at where we use the trigonometric identities. You substitute, you remove what you have, and then you replace it with something else. So let's also look at a situation where we are using the trigonometric substitution. Okay, please, there are a lot of examples that I've put in your notes, so which I you are required just to go through and then see how far you can go in terms of solving. If you have challenges, please we'll discuss them on Friday. I need to finish this tomorrow. Tomorrow we need to finish this so that Friday we just need to revise. That's my target. Okay, now let's look at this. Let's look at a situation where this is part 3, where we use trig substitution. The second part, the first part was algebraic substitution. The third part was a situation where we employ the use of trigonometric identities. Now this third part is where we use trigonometric substitution. Okay, so I'll just go direct. So there are some questions where you can't employ, you try to use the identities, doesn't work. The trigonometric identities, it will not work. You try to use the algebraic substitution, it doesn't work as well. So the best thing that you need to do is to use the trigonometric substitution, where you substitute where there's x, you substitute with either the cosine or the sine function or the tan function, or these others, the sec function, the cosec, or the cot function. So depending on how the question has been given, So you should be able to tell what type of a function should I use to substitute here. Now, the kind of substitution is not just, you just look at the question and then you say, no, the kind of substitution that I need to use here, to employ here, is I need to substitute with the tan, or I need to substitute with the cosine, or with the cot. No. You need, you remember I mentioned to say, we did the derivatives of inverse trigonometric functions. Those are the concepts, those are the things that should come to your mind. When I differentiate the cosine function, the inverse of cos, the cos inverse of x, what do I get? When I differentiate the inverse of the sine function, what do I get? When I differentiate the inverse of the tangent function, what do I get? Those are the things that needs to be in your mind. Those are the formulas that you need to recall. Now, let's look at, now, like I mentioned, the first example is a situation where, this is example number 33, where you substitute, you use what? We are using, okay, let me just put it as a heading. Under this, I'll put it as 3.1, where we are using the sine and cosine substitution. So the first one, part 3.1, we are using sine of x and the cosine of x substitution. Okay, an example. This is example number 32. This example says, find the integral of 1 over the square root of a squared minus x dx. If you look at this function, the type of a function that was differentiated to get 1 over square root of a squared minus x is either the cosine function or the sine, the inverse of the cosine function or the inverse of the sine function. Now, for now, so this is the only idea that we only have as at now. Now, how will that, what is the structure of that function? Still, we are going to employ the method of substitution either way here. That's the method we are going to employ here. So to do this, let's look at the solution. On each scenario, I'll only give two examples. Please, only 2 examples. Then I'll go to trigonometric where you substitute the tangent. I'll also give 2 examples. Then that will be the end. So I'll look at my time. If I can still have some time, but of which I don't have, maybe integration by parts, we can do it tomorrow. Then we'll look at some after we do integration by parts tomorrow. The same tomorrow we'll look at some applications of integration which are very short. It's a short scenario. Maybe tomorrow we can have the whole. We can learn in the morning and in the afternoon tomorrow. But for today, we can just learn in the morning. Yes. So let's look at this. Now, if you have such a scenario, in such cases, where there is x, supposed to be x squared, sorry. Where there is x, you say let x be equal to the sine of theta, not the sine of x again. You will confuse yourself. Let x be equal to the sine of, not the sine of theta. Let x be equal to a times the sine of theta, where a is just some real number. Then, if this is the case, then the derivative of x with respect to theta will be equal to A times the cosine of theta, which will give, okay, which implies the derivative of x is equal to A, the cosine of theta, d theta. So this is the scenario that you're going to have. Now, hence, now why are we employing this? It's because if I ask you, can you manage to differentiate this, integrate this? It's impossible to integrate it. So the best thing you can do is you need to bring in trigonometric substitution. Hence, the integral of 1 over the square root of a squared minus x squared dx, this is the same as the integral of 1 over the square root of a squared minus, where there is x, we substitute a sine theta. So it means you are going to have a sine theta, where there is dx, we substitute it with a cos theta d theta. Okay. Now, this one was squared. So this will give us the integral 1 over the square root of a squared minus a squared, the sine squared of x. So, moreover, this a, this times that to give us, on top we are going to have a times the cosine of theta, the theta. Oh, here we have theta. If you look at a is common, so we can factor it out. So this is the same as the integral using the rule of sines. The rules of sines, this is the same as the square root of a squared times the square root of 1 minus sine squared of a d theta. Okay. And this is going to give us now 1 minus sine squared of a, using trigonometric identities, this is equal to cos squared of, this is cos squared of theta, but the square root of a squared is a. So at the end of the day, at the end of it all, we are going to have a cos theta over a times the square root of cos squared of theta d theta. Cos squared of theta is just the integral. Now, a and a will cancel, so we have the cos theta over the cos squared of theta, to be cos theta d theta. Okay, maybe we can leave the a there just for argument's sake. Now, this will give us the integral of d theta, which is 1, which will give us theta plus C. Okay. Now, the issue here is that are we done with the construction? The question is, are we done with the construction? So what you have come up with is that the integral of 1 over a squared minus x squared dx is equal to theta plus c. But the question is was our variable of integration theta, or was our variable of integration x? The variable of integration was x. So this is where now, since you now change, since since x, you said x was equal to what? Sine theta. We said x is equal to a times the sine of theta. That's what we said. If this is the case, then if x is equal to a sine theta, then it means the sine of theta will be equal to what? X divided by a. So x divided by a when you divide through. What does this mean? This means theta is equal to what? The sine inverse of x over a. Theta is equal to sine inverse of x over a. So when you substitute now this theta, where there is theta in your solving, you substitute now sine inverse of x over a, what you are going to get is what you are saying is that hence the integral of this 1 over the square root of a squared minus x squared dx, which is we have found as theta plus c, where there is theta, we are going to put sine inverse of x over a plus c, where c is a constant. I can assure you, if you differentiate this, you are going to get that. Okay, I guess everyone is following and you are able to see what I was solving. Okay. So you can also make substitutions with respect to, you can do this kind of substitutions also with respect to cosine. You can also use the cosine function. That's not a problem. Provided this kind of a function that has been given is in this form, you can either use the cosine substitution method or you can use the sine substitution method. The final answer that you're going to get will be the same. There will be no difference. Okay, let's look at another example. This is the last example under this, which is example number 33. We are saying evaluate the integral from 0 to 4 of the square root of 16 minus x squared dx. Okay. So basically, what I'm from doing is just the general form. This is the general. If you look at this, the square root of a squared minus x squared, this a squared is equal to 16. The x squared is the same. So it's just like, so in this scenario, you need to make sure that you rewrite it. It looks similar to the what we have been given in the general form. Now, let's look at the solution. Okay, the camera is not okay. Okay, let me just I guess you are now able to see. All right. Let's look at this example. So the integral from 0 to 4 of the square root of 16 minus x squared dx. This is the same as the integral from 0 to 4 of the square root of, this is the same as 4 squared minus x squared dx. I guess everyone is following. This is equal to sorry for I think if you could see, there's a typo with respect to what I gave and what was supposed to be the case. Sorry for that. We are supposed to have 1, not what I've given. It was supposed to be 1. Okay. So let x equal to 4 times the sine of theta, then dx is equal to 4 the cosine of theta, the theta, and theta is equal to the sine inverse of x over 4. Hence, the integral from 0 to 4 of 1 over the square root of 16 minus x squared dx, this is equal to the integral from 0 to 4 of 1 over the square root of 4 squared minus 4 times the cos squared of the sine squared of theta multiplied by 4 times the cosine of theta d theta. This is equal to the integral of 4 times the cosine of theta over the square root of 4 squared times 1 minus sine squared of theta d theta, which is just the same as 4, the integral of 4 cos theta over 4, when you use the rules, times of indices, 1 minus sine squared of theta, the theta. Okay? Which is equal to the 4 and 4 will cancel, the integral of cos theta over the square root of the cos squared of theta, the theta, because 1 minus sine squared of theta is cos squared of theta. So this is going to give us the integral of cos theta over the cosine of theta, the theta, which will give us the integral of 1 d theta, which is equal to theta plus c, but theta is, oh, I think I've forgotten the limits, sorry, 0 to 4, 0 to 4, 0 to 4, 0 to 4, 0 to 4. Now, I don't need the c, so this will give us theta from 0 to 4. Okay, now, but what is theta? But theta is equal to sine inverse of x over 4. So this is just equal to sine inverse of x over 4 from 0 to 4. And this is going to give us and this is equal to, when you substitute a 4 there, what we're going to get is sine inverse of 4 over 4 minus sine inverse of 0 over 4. This will give us 0. So we just remain with sine inverse of 1. Sine inverse of 1 is equal to what? What angle will give you 1? Is pi over 2. That's the only angle, that's the angle that will give you 1. So it's pi over 2. Or in degrees, 90 degrees. Sine of 90 is 1. There are a lot of examples that you need to go through at your own time, which I've included in your notes. There is example number 33. There is a typo which I need to rectify and send back the notes, please. Yeah. Either way. Now, so you need to look at a lot of examples that involves trigonometric substitutions. Now, I need to go to a situation where the type of substitution that we need to make is the tan of theta. The substitution that needs to be employed is the tangent of theta. Still, I'm going to start with the general form, please. I need to come out of, so I'll just do the general form. Then that example which is given in your notes, you can just go and handle it. So under this 3.2, where we substitute using the tangent function, so 3.2, using the tangent of theta substitution. Okay, so we are now looking at a situation where we use the tangent of theta as the trigonometric function of substitution. Now, an example is, which is example number 34. This is where we are employing the substitution of tan theta. So, this example says, find the integral of 1 over a squared plus 1 dx. So whenever you see something which is similar to 1 divided by a squared, a constant squared, plus x squared plus x squared, just know that the kind of substitution that I need to make here is the tangent substitution. So let's look at the solution. Because we can't differentiate, because we can't integrate this function, the question is what function was differentiated to give us 1 over a squared plus x squared? That's the function we need to find. Now, if in this case, you are going to let x, where there is x, you substitute with a times the tangent of theta, then your theta is going to be the tan inverse of x over a, and your theta is going to be the tangent of x over a, and the derivative of x with respect to theta is equal to a times sec squared of theta, of which this will give us the derivative of x will be equal to a sec squared of theta d theta. Thus, when we substitute, thus the integral of 1 over the square of a, 1 divided by of the square of a plus the square of x, this is equal to, this is just the same as the integral 1 over the square of a plus the square of a times the tan of theta, everything squared, multiplied by, where there is a, sec squared of sec squared of theta d theta. Okay. Hence, this is just the same as the integral of a sec squared of theta over a squared plus a squared times the tan squared of theta d theta, which will give us the integral a sec squared of theta over, since a squared is common, we have a squared outside, we have 1 plus the tan squared of theta d theta. But using trigonometric identities, 1 plus tan squared of theta is sec squared of theta. So by trigonometric identities, c is equal to the integral of a sec squared of theta over a squared sec squared of theta d theta, and this is going to give us the integral 1 over a d theta, which is equal to which will give us the integral 1 over a times the integral 1 d theta, which is going to give us 1 over a theta plus c. But then theta is equal to what? So it is 1 over a times the tan inverse of x over a plus c, because theta is the tan inverse of x over a. All right. Maybe we could say this is the end of this class. I think I'll end here. Maybe we can meet tomorrow at 9 hours. Tomorrow I don't have any other class. So we'll start our class at exactly 9 hours. Please make sure that you attend. And I wish to inform you that on Monday, we are going to have our test 2. Monday test 2. Now, and I wish to inform you that please make sure that you have bundles on that day, a lot of bundles, and you go to somewhere where the internet is strong. I don't like unnecessary cause to say, no, I don't have bundles. That's not an excuse we can give. Okay, so enjoy your day. Thank you so much for all those who have attended from the beginning of the session up to the end. So when we meet tomorrow, we are going to look at integration by parts and also the integration of partial fractions. Then we are going to look at, that is in the morning. In the afternoon, we are going to look at the applications of integration. Okay. So on Friday, we'll look at applications of differentiation. That will be the end. And in the afternoon Friday, we are going to solve all the questions which are in the tutorial sheet for integration for differentiation. We are going to sample questions from there, and we are going to solve all those questions that you are going to find challenging. Please, Friday in the afternoon will be for revision. I'm going to revise all the questions in the tutorial sheet for calculus. Make sure that you bring questions. Even if you find a question somewhere, please bring it. You post it in the group in advance. I'll download that question so that when we meet on Friday, it will just be a revision. Thank you so much. Enjoy your day and your lunch.